Hi, this is Team 21043, High Precision Body Mounted GPS System for Large Mining Trucks. Our team members include...
Hi, I'm Cole Anderson. My degree is Mechanical Engineering.
Hi, I'm Richard Gospoderic, majoring in Mechanical Engineering.
I'm Aziz Tayyar and I'm studying Industrial Engineering.
I'm Morgan Wheeler and I'm studying Mechanical Engineering.
My name is Juan Correa and my major is Systems Engineering.
Hi, my name is Ryan Svedberg and I'm studying Electrical and Computer Engineering.
Team 21043 has been tasked with redesigning the mounting system on Caterpillar's large mining trucks for their high-precision GPS system. The purpose of this system is to be integrated into their mining system for control of the truck's positioning. With the GPS system, it allows the coordinator to know the exact location of the mining truck relative to all other equipment in the field, and maintain its position where instructed. This will allow for more efficient mining operations, along with added level of safety to all workers on site. The system is to maintain constant GPS contact with the satellites, resist weather and debris created through mining and loading operations, and mount it onto current vehicles with very little to no modifications required.
The major requirements from Caterpillar for this project were that the frame shall be rugged and mounted to the dump body instead of the truck frame. This shall be done to keep the assembly out of the operator's field of view, allowing for a safer operation. Since the structure will now be moving with the dump body, we shall make sure the antennas always have a 360-degree field of view of the sky. This shall maximize satellite signal and reduce positional error. And finally, we shall provide a design that is easily serviceable from the engine platform by 2 or less people.
On to point design, the Trimble Zephyr 3 rugged antenna will be used. This will be provided by Caterpillar, as they have these down at their facility, and we'll be using a 3-inch mass mounting system. Furthermore, into the auto leveling assembly, this will be mounted underneath the dump body. This maximizes the field of view for the operator. We have 2 CAD models showing one with under the canopy, one without. When the models were designed, we used FEA, finite element analysis, to determine our structure. We ran through hand calculations and MATLAB code to find the deflection points of our structure. Furthermore, into the sub-assembly, the PA10 linear actuator with a 4-inch stroke is used, which gives us an IP rating of 68. The perforated tube will allow water and debris to escape. Now we get into the drawings. Here is the bill of materials, just to show all the components that go into our build. Most of our steel we bought and cut and fabricated ourselves. Again, into the sub-assembly, we have the bill of material as well. This just shows all the components that are going into our system. Some were bought off shelf and the others, me and a couple other students, built inside the shop.
Here I will go over the electronics side of the point design by using a block diagram as seen here to explain the system we have developed more in depth. The block diagram has been divided into 4 sections. In section 1, we can see a power source for the system. A 24-volt DC source has been supplied to give power to the system. Some components run natively like the linear actuators. However, others like the microcontrollers and the winch that is used for single-person serviceability use regulators to run off of 12 volts. For section 2, there are 2 accelerometers within the system. They are both mounted under each of the 2 antenna mounting brackets respectively to match the antenna's angle compared to the ground. For section 3, there are 2 motor controllers in the auto leveling system. Each motor controller has a microcontroller that they work with in order to take information from the accelerometer and drive the actuator to correct the antenna's angle. Each of the 2 microcontrollers share identical setups. For section 4, the antennas will be mounted to a moving mounting plate along the accelerometers that hinges on the entire frame, allowing them to adjust their position when the dump body is moving via the actuators. The actuators and the accelerometers are wired to their respective microcontrollers in charge of driving that actuator.
This is behind the scenes of our build structure. Currently we're here with a crossbar that will be mounted to the canopy down at Caterpillar's mining trucks. Below here we have the hinges, which are welded on for a serviceability method to allow the structure to lower. In order to lower it, you're going to need to pull these pins, which will release it from the canopy, as these are attached to the canopy as well. Furthermore, we have a winch which will help lower the structure since it is heavy, and the Caterpillar guys can lower it with ease and no one will get hurt. Coming up to the front of our structure here, we have the auto leveling assembly. Right here it is in the upright position at about a 90-degree angle. We have linear actuators with IMUs that control the angle of the auto leveling assembly. As the truck raises the dump body, it will want to self-level with the dump body. So for example, if the truck is on a flat surface, it's going to be on the down position horizontal with the Caterpillar antenna as shown here. So these are controlled from the black box, and these control the IMUs and all the electronics, which will be protected with the Pelican case as shown.
Issue we ran into recently was that our linear actuators broke. They stopped working in the structure. We were testing the auto leveling system, doing the maintenance method, letting it go up and down. But when we fully closed it, it started making a weird noise. We decided to disassemble it from our structure itself and then see if it would run without it being mounted.
Over our system requirements, we had a table of all our requirements. We separated them into subcategories, starting with our general requirements in 4.1, moving to our electrical requirements in 4.2, where the signal shall not drop more than 3 dB inside the coaxial data cable. That's one of our electrical requirements. Moving on to our structural requirements, on the next slide, we have 3 of them actually listed here with their verification method and the summary. And then after that, we will have the 4.4 visibility requirement, where it shall meet the visibility ISO 5006 and 14401. Moving on to the next slide, we have our 4.5 physical interfacing requirements. It goes from 4.5.1 up to 4.5.6, so there are 6 sub-requirements within that category. And then moving on to 4.6, our access system requirement, and finally the paint requirement in 4.7, where the system shall meet CAT yellow surface finish requirement.
So here we're going to discuss our budget summary. Going into the project, we were given $4,000 to complete the project. So we had to take this into consideration for the design and be mindful and conservative with our spending. Here at the tail end of the project, the team has spent approximately 95% of the budget just for easy numbers' sake, which translates to $3,811.88 in spending on materials and services.
For lessons learned on this project, we're going to talk about the project overview. Our issues were auto leveling design complexity. We thought we would possibly using stepper motors and gears to make it complex and an issue. However, when taking a second look back at it, we found out that we could use linear actuators and a hinge to replicate the same idea. Overall for the project, we had our mechanical design. The structure was implemented as a static or auto leveling system. It was a good feature for our design. For the electrical design, we had an auto leveling system that was simple to control and very straightforward. This is our project. We hope you enjoy it and glad you listened to our presentation.